There, now I've got the mic actually turned on. Last time we were talking about this weird phenomenon. Of course, 3.3 is not the same thing as 3.299999999999999982224. I think I said the right amount of nines. What's going on? Anyone have any idea? Raise your hand if you think maybe you have an idea. One, two people maybe. So, we've got a bit of a problem because as we saw at the end of last class, remember how I was saying like, okay, if we're talking about integers, what comes after 1? Somebody yell it. What comes after 2? Exactly. And if I ask you what comes after 1 billion, you say 1,000,000,001. If I say 1 trillion, you say 1,000,000,001, and so on. We could just keep going bigger and bigger and bigger. But as soon as we start to talk about real numbers, numbers with decimals and whatnot, we've got the problem. What comes after 1? 1.1? Well, 1.01 comes before that, and 1.001 comes before that, and so on. So it's kind of like we've got like infinity in 2 ways, you know? We've got infinity because we can just keep counting up. But we can also get infinity because we can keep making smaller and smaller and smaller decimals. In the computer, we have, by the way that our computational systems that we use, those laptops that you all have and like I have there, they're limited in that, you know, we use zeros and ones to represent numbers. And we have a finite number of zeros and ones that we can use to represent values. In fact, in your typical programming language, like, let's have a look here. We can ask Python what its maximum integer is. It looks like in Python 2, Python 3 might be slightly different. Let's see. So it looks like maybe if I do something like this, where on earth did my collab? Oh, here it is. Let's go down here real quick and import. So it looks like, what is this? Like, if we're asking the maximum size, let's not worry about the type of this thing that we're talking about size, but there is a fixed size. There is a largest integer that we could like store. Anything beyond that, we run into problems because we run out of zeros and ones to represent the numbers. So, you might remember, I think I was talking about this in this class. You might remember, did I talk a little bit about binary before? Yeah, and how we count in binary like 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and so on. So we have these, what we call like bits. And we can represent a number, or really any value we want in the computer, with these bits. In fact, this is a 1, 2, 3, 4, 5, 6, 7, 8. Anyone know what we call 8 bits? Somebody yell it. Anyone know what we call 4 bits, or half a byte? This isn't a joke. No one knows? It's a nibble. That's not a joke, it's a thing. I love that. That just, oh. Anyways. So if I write this, that means 0. I mean, there's a lot of leading zeros. I mean, at this point, you don't even know if this is in binary and base 10, right? Just a whole bunch of zeros. I mean, leading zeros are useless. But if I do this in binary, what value is this? Anyone know? It's 1. Anyone know what this one is? Well, 1, 1, yeah. But what does it mean in decimal? 3. Because this is like the 1's digit. Well, there's a 1. And this is like the 2's digit. There's a 1 there. So 2 plus 1, and so on. This right here is the maximum, like whatever this number translates to in decimal, is the biggest number I can represent with 8 bits, 1 byte. And this assumes that we don't have signs as well, like is it positive or negative? So let's do a quick little Google search here, because I'm lazy. 1, 1, 1, 1, 1, 1, 1, 1. I guess 255. That number right there is 255. I can't represent the number 256 with 8 bytes. I can't. Typically, when we're programming, we'll have a couple of bytes, a lot of bits to represent numbers. For example, what if we have 2 to the power 32? That would be equivalent to how many, if we had 32 ones, what number would that mean? Well, assuming we don't have negative numbers, that would be 4,294,967,296. If you wanted to represent 4,294,967,297, you can't. You can't represent that number with 32 bits. Right now, I'm just talking about integers. Imagine now we have that added complexity of decimals. We're running out of zeros and ones to represent a lot of unique values, aren't we? So, it's a consequence of this, it's a consequence of this issue why we have what we call floating point precision problems. Floating point numbers, and there's a lot of tricks that your computers do to represent floating point numbers properly. And you'll learn all about that next year if you're in computer science. But we've got a problem. We don't have enough bits to store all this. I mean, the more bits we have, the more we can represent, right? But we're still limited. And it's that causes this issue. Oh, right here. I guess we couldn't represent that value, 3.3. We just can't. It sucks, but we can't. So imagine you wrote some software. Maybe you're a chemist and you're dealing with a lot of decimal points and whatnot. I don't know. And you want to check if your calculation comes out to 3.3. Let's try. I'm going to go down here, add a thing of code. Does x equal 3.3? Oh, did I not run this? Now Python 3 is actually doing us a bit of a favor here. Because I guess it's kind of filling in the blanks a little bit. You know, the decimal's so small, is it equivalent, whatever, you know. But obviously we know in reality these things aren't the same. Other programming languages, I type this in, it's going to say, nope, they're not the same. In fact, what happens if I do like 2.299999999? Well, hold on a second. X actually is a heck of a lot closer to 2.99999 than it is to 3.3, but this is saying false. So we're in trouble here, aren't we? We are having a real hard time checking if floating point numbers are the same. But there's a trick. By the way, I'm just telling you this now because if and when the time comes, you'll know how to deal with it. This really isn't going to become that much of a problem for 161. But there is a trick to check if floating point numbers are the same. Or perhaps maybe I should word it, if they're close enough. So in real life, I'm a chemist, I'm a physicist, I have measuring instruments, let's say. And I'm just giving you this as like a why we can justify doing what we're doing. Maybe it'll be intuitive and you don't need the justification, but I'll explain it anyways. You're a scientist and you've got your instruments for measuring things, right? And you come along and you measure something, but you know, my measuring device is only so accurate. Like maybe I've got a ruler that goes down to millimeters, but anything beyond millimeters, you know, I can't really measure. Maybe I have like a micrometer. What do you call those things that measure really small things? A micrometer, there, great. Let's say I get that, we can measure more than millimeters. But I still only have a couple of decimal places. Maybe I've got a really good recording instrument that can record 6 decimal places. That's a good precision, right? In real life, that's a pretty darn good precision. But anything beyond 6 decimal places, I'm kind of guessing. You know, maybe I'm eyeballing going like, it looks like it's halfway between those two. Maybe I can squeeze out an extra half decimal place or something. I don't know. But the reality is I do have a limit. So here's what we can do. What if I say, I'm going to say like, okay, y equals this. Oops, 7. What? There, false. What do we think's gonna? What if I do? One. What? The difference between.
Oh, 3.9.
Oh, that's supposed to be a 3. Oh my goodness, now I'm ruining everything. Let's get less decimals. There we go. How many decimals do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's way beyond my instrument's measuring ability, right? If I calculate the difference, so I'm not checking if 2 things are equal. What I want to do is take those 2 things, find out the difference between them, and if the difference between those things is less than a certain threshold, I call them the same. If that doesn't make sense, slow down and think about what I'm saying. I want to know if these 2 values are the same. We know with floating point numbers we might run into an issue. So what if I don't actually really care if the numbers are the same? What if I care they're so friggin' close, we might as well call it the same. Look at the difference between x and y. 1 times 10 to the negative 11. Negative 11. That is such a small value, call it the same. We'll say it's close enough, especially considering my instruments aren't that accurate. And we've got this issue with floating point numbers. So here's what I'll do. I'll say, is the difference less than, and technically we should probably do the absolute difference. We don't want negative values throwing things off. If the absolute difference between these 2 values is less than some threshold, my measuring device was 6 decimal places. There. 1, 2, 3, 4, 5, 6. Let's add an extra 0 for good measure. Ah, there we go. Problem solved. So this is one of the many possible tricks we could do for checking for equivalency in floating point numbers. It's not if they're equal, it's that if the difference between them is so small, we call them close enough. Any questions about that? So what we learned a little bit about right now is, well, I mean, we have a discrete number of bits, a finite number of bits to represent values. But we have infinite number of floating point numbers. In fact, we have like a weirdly big infinite number, right? Because we've got infinity as it grows and infinity as we take smaller cuts. So we've learned a bit of a trick to address this. Any questions? Yeah.
How come when you have like 6 zeros and 1 1 equal to string?
I can't hear you.
How come when
Maybe just if you.
how come when at the beginning you have 6 zeros at the bottom and then 1 1 that's equal to string? At the board.
Right here?
No, at the board. Yeah, when you had 6 zeros and 1 1 and you said equal to string. How does that happen?
6 zeros and 1 1?
Yeah.
There were 2 ones. That is 3. So this is what your question is like, why is that 3? Well, this is just how like binary works. So let's skip this for a second. I'm going to go here. Binary works like this. And just, if I write the number 151 in decimal, that's 151, right? If I say that's still 151, these zeros are useless. It's the same thing here. We can like ignore these. Pretend they don't exist, they don't affect the value. So, here's how it works in binary. This is 0. Why? Because 0 is 0. What comes after 1? Even in base 10, it's the same. I meant to say 0. What comes after 0? 1. Okay, great. That's 1 in binary as well. Now in decimal, we have 10 symbols that mean 0 through 9, right? And that's base 10. But we've got a problem because you've probably never thought about decimal numbers this much. Base 10 numbers. Once we hit 9, remember the symbol 9 means the value 9. What symbol comes after 9 in base 10 to mean the value 10? 1 0. So there's not one symbol anymore, right? You needed 2. You needed to move a 1 over, add 1 to the next the next digit place, and turn this one down to 0. So in base 10, once we got to 9, that is equivalent to 1, 2, 3, 4, 5, let's do 5, 6, 7, 8, 9. I'm doing like lines to kind of show how the symbols and values can be represented differently. And if I want 10, well, there is no one more symbol. So the rule is add 1, okay, turn this to a 0 and add a 1 there. Because really this is like a 0 in front of it. So turn that 0 to a 1 and reset this to 0. That's what we do when we run out of symbols. Binary. We have 2 symbols, 0 and 1. The rule is the same as with decimal. I've run out of symbols. I have no more symbols left. But I need to represent the value 2. So this is like nothing. This is the value 1. I want to represent 2. Don't think this is binary. That's not binary at all. Think of this as like, in grade 2 when you learn how to count with, groups of 5. But how do I represent 2? I don't have the digit 2. So we follow the rule. Remember, there's actually a 0 here. Turn that 0 to a 1. Reset this. That's 2. Now I want to increase this value. Okay, well, 1, 1, because what comes after 0, 1. That's 3. Now I want to increase this to 4. But again, I'm out of symbols. So what do I do? And also remember, there's actually zeros out front here. We just kind of ignore them. So what are we going to do? Well, okay, we ran out of digits, so we turn that to a 0. And we want to add 1 to here, but we ran out of digits. So we got to reset that to 0. Add a 1 to this, there. That's 4. So that's binary. You're going to learn, we don't really need to worry too much about binary counting in 161. Not even in 162, really. But you'll learn and think about it a little bit more if you're in computer science and you keep going. And the reason we like binary in computer science and in programming and for these computational systems is we have an easy way to represent a 0 and a 1 physically. Low voltage, high voltage. And it's just a whole bunch of low voltages and high voltages that make all your computers work. So you know how we say computers, it's a bunch of zeros and ones. Well, really, physically, it's a bunch of low voltages and high voltages. 0 means low voltage, 1 means high voltage. So if we go through and look at these little groups of transistors, and we see low voltage, high voltage, low voltage, high voltage, we can decode that to mean something. So does that answer your question?
Yeah.
That was a long-winded answer to a very simple question.
That's okay, thank you.
Any other questions? All right. All right, yeah, that's that. Okay, so this right here is more or less a review of what we already talked about, so we'll blitz through this a bit. 5 greater than 2, well, that's true. 5 less than 2, that's false. Just like I was saying before, less than, greater than, equals, those are operators, but they take 2 values and return a Boolean. So it's kind of like plus, except plus works on numbers and gives you a number. Less than works on numbers and gives you a true-false value, a Boolean value. So let's do a quick little example here. Don't look at the thumbnail because it gives it away. Write a quick little function, is negative. And it'll return true if the value is negative and false otherwise. This should be a really easy one. So write this quick little function and test it a couple of times, make sure it works. I'll give you a minute to work on this one. You should absolutely be able to get this, so I want to give you a minute to make sure everyone gets a chance to get it, because I know you know how to do this. Raise your hand if you got it. Raise your hand if you need like just one more minute. I'm like there. Okay, keep going, keep going. All right, I'm going to code one version of this up. If n is less than 0, return true, else, oops, there. There's my implementation. Who's here looked more or less like this? Good, this is absolutely correct. And let's just test it to be sure. Let's say is -1. -1. Let's put like a 0 in here, see what happens. It's always good to check edge cases, you know? So we should see true, true, because 0 isn't negative, I guess, you know? And then, actually no, we should see false, false, true. Good, good. And the 0 is what I meant by an edge case. You know, it's kind of in between. What's it going to do? Is that right? Think about those things. So there we go. Great. Cool. So we've seen how, so I've already talked about how, you know, when we're running through a function, when the code's executing, as soon as it sees a return, the function stops executing completely. And if you're still left scratching your head a bit about that, thinking like, well, hold on, in that example I just showed, you had 2 returns. There's 2 returns here. How can we have 2 if only 1 can ever be hit and then immediately it stops? That's because the if condition never got triggered, or the else condition never got triggered. Let's look at the second return. Return false. If n is -1. If it's any negative number, it goes inside there. It executes that code. But if n is bigger than 0, pardon me, bigger or equal to 0, it never executes line 3. It never runs that code. It's not that our functions can't have more than 1 return. It's that our function will only ever be able to execute one of the returns at a time. Because as soon as it, like if n was negative, it hits line 3, and it just immediately stops. So because of that, we can use that if we really want to do something like this. And I did show you this last time. Because if the value is negative, it hits return true, and then the function stops immediately. If it's positive, it never executes line 3, and then it jumps down to line 4 and carries on. Logically, this and the other are equivalent. This and this, same difference. Oh, there. Then we can test it. Good. Any questions about that? Because I know this can trip some people up. Just note, you can have many returns when looking at the code, but once the code's running, it'll only ever hit 1 and then stop. So do this one here. And I'll remind you of that mod function. Write a function. Oh, I guess not even write the function. Take that function. Just take this function and copy it into your code. And just do this little activity. See if you can get all the steps done. I'll give you a minute, because this is a kind of a tricky one. Or not so much tricky, but fun, interesting, I don't know. Who here's done the not divisible by? Really high, I want to see. Who here's like still working on it, but you just need a second to get not divisible by? Okay, cool. I'll give you a minute to do that, and then I'll go over the not divisible by, and then we'll carry on with the other stuff, like the next 2 points. If you're past not divisible by, carry on, keep doing what you're doing. Okay, I'm going to do the not divisible by. And I'm really lazy because I'm a computer scientist. So here's what I'm going to do. Is I'm going to take divisible by and I'm going to modify it a little bit. And I'm curious which way people did this. And this might be the first good example where you can see how different code gives you the same thing. Because remember before I was saying as your programs get more complex, your code could look very different from one another, but you could both be absolutely correct. So, here's what I'm going to do. I'm really lazy. I'm just going to do this. Who here did that? Raise your hand. Yeah, really high. So here's probably your thinking. Well, if it is divisible, I don't want to return true. I want to return false, so let's just change it to false. Great. So pat yourself on the back if you did it that way. Good job. So I'm going to put this back. Anyone do this? Raise your hand really high, I want to see. So this is equivalent. This does the same thing. Now some of you may not know or remember, I don't even know if I talked about it. Equals equals asks if two things are equivalent. What does exclamation point equals mean? It asks if they're not equivalent. That's what you're going to say, right? I took it away from you, sorry. Great. So if you did it this way, good job. How about this? Who did this? Not. Well, I guess I didn't actually run it, but not. Did anyone do it this way? No, no one? Well, that's okay. All I did is I asked the question and then wrapped it in not. This is kind of like almost exactly the same thing as the exclamation point equals, the not equals. This checks if they're equals, and if it's true, we not it, we get false. And if it's false, then we not it and give it true. So we ask, is it not divisible by 2? Is it not the case that A is divisible by B? That's what it said. Yeah?
What I did is I actually called the divisible by function, and I just inverted by it.
Yeah, so an alternative is this. And this will work as well. So raise your hand if you did it this way. We've got 1, 2. Great. This is absolutely fine. I need to write a function that checks if it's not divisible by something. I have a function that tests if something is divisible, so I'll just ask the function to tell me if something's divisible, and if it is, just return the opposite. Yeah?
Could you do it by writing the function not divisible by and then saying if A divided by B equals, say, a float, and then return something? Could you do it like that or no?
But what if it is not a float, but you get a nice whole, like what if the remainder is 1? It's not a float.
So you could do it so like if you made it the answer string was a decimal return this.
Well, because 4 divided by 3 is 1 remainder 1. So it would say, oh, it's a nice whole number, but it's not actually divisible. But good to think. A better way to ask that question is to try it.
I did.
Okay, cool.
And I didn't know if I had a syntax error.
Gotcha. Cool, so this is absolutely fine to do it this way. Go ahead and do it that way. Fantastic. So let's go back, and if you're done, great. If not, work on these two here for a second. See if you can figure it out with one return statement. That's not too hard. But perhaps the slightly more difficult one is write it with only one line of code. But okay, do me a favor and don't do what I just did though. Don't do this one. This is not what I want. See if you can write in one line of code a different way. For the sake of time, let's just do this one real quickly together. Here's what we can do. In fact, for simplicity, because the not kind of throws us off, I'm going to change the divisible by. Let's think for a second about what we're looking at. I say, if A mod B equals 0, when will line 3 run? Well, line 3 only runs if that condition is true, right? So if the condition is true, if that question gets evaluated to true, what do we return? Everybody yell it. If that question evaluates to false, what do we return? Wait a minute. If the question comes back true, we return true. If the question comes back false, we return false. If it's true, return true. If it's false, return false. Well, hold on a second. What if I do this? Get rid of all this nonsense. Let's test it. It works. If your mind is blowing, you're thinking too much. Slow it down. All this function does is say, return the result of A mod B equals 0. A mod B equals 0 is only true if the thing is divisible by, if A is divisible by B. So if all of that, if A mod B equals 0 returns, gives us back true, I want to return true. If the question gives us back false, I just want to return false. If you're left still going like, wait, what? It's out of print here. And I'm going to add like a tab or something. There. So, the first time I called it with 4 and 2, A mod B is 0. That would mean A mod B equals 0 is true. So, when it's true, return true. When it's false, return false. There's no need to have the if true, return true, else return false, because the true means true and the false means false. It's like we're cutting out the middleman here. In fact, doing it this way, you won't lose marks if you do it this way, but for programmers, this is like a meme, where it's like, if true, return, Don't do it this way. You can do it with the one return and it works just as well. Programmers will laugh at you. They'll make fun of you if you do this. Even though there's nothing wrong with it, you get your big job at Amazon once you're done. You write this code, all your colleagues will make fun of you so bad and no one will like you. Don't worry, you're just learning. I'm teasing you. But you can do it with just the one return. If you're scratching your head, slow down. Think about it logically, step by step. If you're confused, you're thinking too much at once. Questions about this, though? All right, so some people already kind of discovered this. I'm going to take these 3 little functions here. Oh. What's going to happen if I say print type of add 5 and 5? I mean, add 5 and 5 should return 10, right? Because, I mean, that's what this function says. And what's the type of 10? It's an integer. But what happens if I put the name of the function, but I don't give it any parameters, and I don't include the parentheses? Well, suddenly we have something called a function. A function has its own type. It's a function, which is pretty cool. And not a lot of programming languages let you do this. So because of this, I could actually do something like this. And I'm just going to show you for the sake of showing you. Do something. If you look at do something, it might make sense. I want to pass a function and two values. And then I want to return what the function of a and b gives me. So if I say add 5 and 5, it gives me 10. Why? Well, add is the function. A is 5, b is 5. I take the function add and I call it with the values a and b. We just go up here. We call it that way. It's kind of a neat little weird thing we can do. As we go, no one ever sits down and says, I'm going to write a program and just starts. Never happens. That never happens. If you expect to be able to do that, you're wrong. It's like those, and I think the part of the reason why people kind of get in their head, like, oh, I'm bad because I hit run and it didn't work. Well, no, you're going to spend hours debugging. I got an email this morning saying I was trying for like 2 hours and I couldn't get the assignment done. Come back after like 10. 2 hours is nothing. You're going to be spending a lot of time, really taking your time, writing very meticulously thought about code. And I think part of this is, see if I can find an example. I think it's because when you watch movies, and you ever see like the hardcore programmer hacker, it's because you see this like, oh wow, look at me. I'm such a coder, This never happens. Oh no, I broke it. Access denied. Oh, I gotta keep hacking, I guess. This never happens. No one, access denied again. Oh, I gotta keep coding away. Never. This is a joke. You wanna see what a programmer goes like? They go, I wonder, let me write something down, scratch something down. And then maybe after 5 minutes you write like 2 lines of code. That's normal. And what's even more normal is after you write 4 lines of code, you realize it doesn't work. So you got to go back and fix it. That's what you should expect. All right, I'll see you all tomorrow.